Right now, while you're reading these words, something is happening that almost nobody on Earth knows about. There is an object moving away from you at roughly 38,000 miles per hour. It is smaller than a compact car. It weighs less than a grand piano. It is currently farther from the sun than any object human beings have ever built. And every second you spend here, it gets about 10 miles farther away. It is not a planet. It is not a telescope. It is not a satellite in orbit around anything at all. It was built before the internet, before the personal computer, before the space shuttle ever flew. Its onboard computer holds less memory than a single photograph on your phone, and what it is doing right now is quietly breaking one of the cleanest assumptions in orbital physics, the assumption that we know exactly how fast a spacecraft should be slowing down as it leaves the sun behind. The researchers who spent 30 years on this problem were not using words like interesting or unexpected. They were using words like anomalous, unmodeled, and we could not account for it. This is the story of Voyager 1. And here is the part the headlines are not telling you. It is not just what Voyager 1 found out there. It is what the search for its missing deceleration revealed about the physics of heat itself. Physics that applies to every spacecraft we will ever build, including the ones that will carry people. It is what is happening to Voyager 1 right now, in 2026, that almost nobody is talking about. A machine losing about 4 watts of power every single year and running out of instruments to turn off. And it is what is going to happen sometime in the 2030s. A date that is not a rumor and not a prediction, but a straightforward consequence of arithmetic. Stay with me, because by the time this is over, you will never think about that little probe the same way again. To understand why anything is slowing down out there, you have to go back to 1965. And to a graduate student doing math nobody else wanted to do. His name was Gary Flandreau. He was in his mid-20s, a Caltech student working a summer position at the Jet Propulsion Laboratory in Pasadena. He was handed one of the more tedious jobs available: work out the positions of the outer planets over the coming decades and see whether any useful trajectories fell out of it. This was hand-plotted work, curves on graph paper, slow, unglamorous, repetitive, and then the curves lined up. Flandreau found that in the late 1970s, Jupiter, Saturn, Uranus, and Neptune would arrange themselves along one side of the solar system in a formation that would let a single spacecraft slingshot from one to the next, borrowing a little orbital momentum from each planet in turn. A trip that would otherwise take 30 years could be done in 12. That alignment happens roughly once every 176 years. Think about that number for a moment. The previous window opened when Thomas Jefferson was in the White House. The next one opens well after everyone alive today is gone. If humanity had gotten to rocketry a few decades later, we would simply have missed it. We did not miss it. On August 20th, 1977, Voyager 2 launched from Cape Canaveral. 16 days later, on September 5th, 1977, Voyager 1 launched on a faster trajectory that would let it overtake its twin. The names are confusing on purpose. Voyager 1 was second off the ground and first to arrive. Voyager 1 reached Jupiter in March 1979 and Saturn in November 1980. At Saturn, mission planners made a choice that decided everything that followed. They could send Voyager 1 onward to Uranus and Neptune, or they could bend its path upward for a close pass at Titan, Saturn's strange, atmosphere-shrouded moon. They chose Titan. That single decision threw Voyager 1 off the plane of the planets and out of the solar system at an angle, on a course that would take it nowhere near another world ever again. Voyager 2 got the grand tour. Voyager 1 got the exit. And on February 14, 1990, at a distance of about 3.7 billion miles, it turned its camera around at Carl Sagan's urging and photographed Earth as a single pale dot, less than 1 pixel across, suspended in a shaft of scattered sunlight. Then it kept going. It is still going. Here is the part that matters for everything that follows. Voyager 1 has no engine. It has never had an engine in the sense you are probably imagining. It has small thrusters for pointing itself, and that is all. Every bit of its speed was banked in the first 3.5 years of the mission, borrowed from Jupiter and Saturn, and never topped up since. So its motion is simple. It coasts, and as it coasts, the sun pulls back on it. That pull is weak now. Gravity falls off with the square of distance, and Voyager 1 is currently around 170 times farther from the sun than Earth is. The sun's grip out there is roughly 30,000 times weaker than what you feel on Earth's orbit. But weak is not zero. So the honest version of the headline is this: Voyager 1 has been slowing down continuously since 1980. It is supposed to. Solar gravity is still tugging on it, and will keep tugging on it forever, in ever smaller amounts. Voyager 1 is above solar escape velocity, so it will never turn around. It simply approaches a final coasting speed and never quite reaches it. That part is not mysterious. That part is Newton. The mystery is a different one, and it is more interesting. Because for about 30 years, the numbers did not close. Here is the chain, one step at a time. A spacecraft this far out is tracked by radio. You send a signal, it comes back, and you measure the frequency shift. If the craft is moving away, the returning wave is stretched. Measure the stretch, and you know the speed, to a precision that is genuinely absurd, fractions of a millimeter per second. That precision means you can check the prediction. Compute what the sun's gravity should be doing. Compare it to what the radio says is actually happening. And on two spacecraft, in the 1980s, those two numbers refuse to match. Before we get to the mismatch, understand the conditions under which any of this is measured, because they are close to impossible. Voyager 1 is currently more than 15 billion miles from Earth. That number is so large it stops meaning anything. So here is a translation. If you shrank the distance from Earth to the Sun down to the length of a single sheet of paper, Voyager 1 would be about half a football field away. Its radio transmitter puts out roughly 20 watts. That is less than the bulb in a modern desk lamp. That is comparable to the light inside your refrigerator. 20 watts, spreading out across 15 billion miles. By the time that signal reaches Earth, it has been diluted to a level that is difficult to state in normal language. A small fraction of a billionth of a watt. The dish antennas of NASA's Deep Space Network, some of them 70 meters across, are essentially straining to hear a whisper from a machine that left before most people watching this were born. And the round trip takes time. Light speed is not instant at this range. A command sent from Earth takes roughly 23 hours to reach Voyager 1. The confirmation takes another 23 hours to come home, nearly 2 full days for a yes. There is no repair option. There is no second copy. There is no possibility of a rescue mission, ever, because nothing we have built since can catch it. Every instruction has to be right the first time, sent to hardware designed with slide rule-era engineering margins, running software written in a language most working programmers have never touched. And the whole thing is powered by heat. Voyager 1 carries 3 radioisotope thermoelectric generators, blocks of plutonium-238 that produce warmth as they decay, with that warmth converted directly into electricity. At launch, they supplied roughly 470 watts. They lose about 4 watts every year. Every year, without exception. It is the most reliable clock on the spacecraft, and it is counting down. 4 watts a year, 15 billion miles, 23 hours of silence between question and answer. Hold on to those 3 numbers. They are the whole story. Now, the anomaly. It did not start with Voyager. It started with 2 older, simpler probes, Pioneer 10, launched in 1972, and Pioneer 11, launched in 1973. They were the first craft to cross the asteroid belt and reach Jupiter, and like the Voyagers, they were thrown out of the solar system on escape trajectories. At JPL, a researcher named John Anderson tracked their radio signals for years, and beginning around 1980, he noticed that both Pioneers were not quite where the equations said they should be. The discrepancy looked like a tiny extra deceleration, pointed roughly back toward the sun. Something was slowing them down a little more than gravity alone could explain. In 1998, Anderson and his colleagues published the number in Physical Review letters. The extra deceleration was about 8.74 times 10 to the minus 10 meters per second squared. That notation hides how small this is, so let me translate it. That acceleration is roughly 10 billion times weaker than the gravity holding you in your chair. If you started at rest and let it push you, it would take you about 36 years to reach walking speed. It is nothing, and it was measurable, consistent, and present on both spacecraft. That combination is what made it serious. A glitch on one probe is a glitch. The same signature on 2 independently built craft, over years, is a pattern. And a pattern that small, in that direction, sitting in the gap between prediction and observation, is exactly the shape a new law of physics would have if one existed. For the better part of a decade, the Pioneer anomaly was one of the most seriously discussed unexplained results in gravitational physics. The reason is that we already know general relativity and the standard model do not fit together. And we already know that galaxies rotate as though there is far more mass in them than we can see. Physics has open wounds. When something unexplained shows up at the scale of the outer solar system, people look hard at it. Proposals came in from every direction. Modified gravity, where Newton's law bends slightly at very low accelerations. Drag from unseen matter, extra dimensions, effects tied to the expansion of the universe. Some of these were serious papers by serious people. And what is worth noticing, what this channel exists to notice, is that none of them were treated as answers. They were treated as candidates, and candidates get tested. The mundane explanations got tested too. Fuel leaks, gas venting, errors in modeling how the solar system's own mass distribution pulls on a departing probe. And one of the mundane candidates was heat. Recall those generators. They convert a fraction of their heat into electricity. The rest is waste, radiated away into vacuum. Voyager and Pioneer both carry hundreds of watts of thermal power for a few hundred watts of useful electricity. And every watt of that waste heat has to go somewhere. Here is the chain, one step at a time. Heat leaves a surface as infrared photons. Those photons carry momentum. They do not simply vanish. They push, very gently, in the direction they travel. And if a spacecraft radiates more heat off one side than the other, the imbalance produces a real, permanent thrust, pointing the opposite way. The Pioneers had a large dish antenna facing back toward Earth, and Earth was in roughly the direction of the Sun. Heat bouncing off the back of that dish would push the spacecraft sunward, which is exactly the direction the anomaly pointed. The problem was that estimating this properly required knowing, in detail, how heat moved through a spacecraft built in the 1960s and 70s, and knowing how that changed as the plutonium decayed over decades. That work was led by Slava Turyshev at JPL, and it took years, partly because the necessary data had almost been lost. Old telemetry existed on magnetic tapes of obsolete format, sitting in storage. Recovering it, reading it, and reconstructing 30 years of thermal history was itself a small archaeological project. Then, they built a full computational model of the spacecraft. Every surface, every emitting component, every reflection. In 2012, in Physical Review Letters, Turyshev and colleagues reported the result. The thermal recoil force accounted for the anomalous deceleration. Within the uncertainties, there was nothing left over. The Pioneer anomaly was heat pushing on a spacecraft. Now, I want to be careful here, because this is where most retellings of this story go wrong in one of two directions. Either they pretend the mystery is still open, because that is a better thumbnail, or they treat the resolution as proof that the whole thing was a waste of time. Neither is right. An anomaly of 8.74 times 10 to the minus 10 meters per second squared was detected across billions of miles, held up under scrutiny for more than a decade, motivated a genuine re-examination of gravity, and was ultimately explained by a physical effect so subtle that modeling it required rebuilding a lost spacecraft in software. That is the process working, not failing, working. And it left behind something permanently useful. Nobody designing a precision deep space mission now ignores thermal recoil. It is a known term in the budget. It got there because two 1970s probes refused to be where they were supposed to be. So where does Voyager 1 fit? This is the honest, slightly deflating, genuinely interesting answer. Voyager 1 cannot easily be used to measure an effect that small. Not because it is too far, and not because its radio is too weak, because of how it points itself. The Pioneers were spin-stabilized. They rotated like a thrown football, and that rotation kept them steady with almost no active correction. That made them beautifully clean test masses. Whatever pushed on them showed up in the tracking data with very little contamination. The Voyagers are three-axis stabilized. They hold their orientation actively, and they fire small thrusters to do it. Many small pulses spread across decades. Each pulse is a tiny velocity change of exactly the kind you are trying to detect. You are trying to measure a whisper on a spacecraft that clears its throat regularly. So the answer to the question in the title, stated as precisely as I can state it, Voyager 1 is slowing down. That slowing is dominated by ordinary solar gravity. It also experiences thermal recoil forces of the same family that explain the Pioneers, and its trajectory data is not clean enough to isolate an unexplained residual the way the Pioneer data was. There is no confirmed, unexplained deceleration on Voyager 1. What there is a spacecraft whose behavior we can no longer fully characterize, doing something we do not have a second example of. In a region of space we have 4 total data points for. That is not the same as a mystery solved. It is a mystery we currently lack the instrument to ask properly. Meanwhile, the real story of Voyager 1 in the 2020s has been survival. On August 25, 2012, Voyager 1 crossed the heliopause, the boundary where the sun's outflowing solar wind finally loses the argument against the surrounding interstellar medium. Confirmation came later, and it came from an unusual place. Don Gurnett's team at the University of Iowa used the plasma wave instrument to listen for the ringing of the surrounding plasma after a solar outburst reached the spacecraft. The pitch of that ringing revealed the density around it. The density said, interstellar. It was the first time anything built by human hands had left the sun's bubble. Since then, the mission has been a slow negotiation with the 4 watts. In November 2023, Voyager 1 began sending back data that was structurally meaningless, a repeating pattern rather than telemetry. The cause was traced to a failing section of memory in the flight data system. Engineers wrote code to relocate the affected functions elsewhere, sent it across 15 billion miles, and waited roughly 2 days for a reply. It worked. Science data resumed in 2024. That same year, the team switched to a set of thrusters that had not been used since 1980 to work around fuel line clogging in the primary set. Hardware left idle for 44 years, brought back into service by people who mostly were not on the original team, using documentation written by engineers who in many cases are no longer alive. Ed Stone served as Voyager's project scientist from 1972 to 2022, 50 years on one mission. He died in 2024. Suzanne Dodd has managed the project through this period of managed decline, and through 2025, instruments have been shut down one by one, each shutdown buying a little more time for the rest. 4 watts a year. That is the negotiation. That is the whole negotiation. Here is where it ends, and it ends on arithmetic rather than drama. Power keeps falling, instruments keep being switched off. At some point in the 2030s, there will not be enough electrical power to run a single science instrument and still keep the transmitter warm enough to talk. And then, one day, there will be a last signal. It will take about a day to arrive. Nobody on Earth will know it was the last one until the silence has gone on long enough to be conclusive. That is the actual ending. Not an explosion, not a collision, a machine getting quieter until it is quiet. But listen to this part carefully, because it is the part that changes how the whole story sits. When Voyager 1 goes silent, it does not stop. There is nothing out there to stop it. No air, no friction. Solar gravity is already negligible and getting weaker every second. It will continue at roughly its current speed, on roughly its current heading, for a length of time that makes the age of human civilization look like a rounding error. In about 40,000 years, it will pass within a couple of light years of a faint star in the constellation Camelopardalis. Not a visit, not an encounter, just the closest it happens to get to anything. It carries a gold-plated record, with music, greetings, and images from a planet that, by then, will have changed beyond recognition. And it carries something the record does not mention. 3 generators that will still be radiating a trace of waste heat, still pushing back on the spacecraft with a force too small to name, exactly as they did when they confused a generation of physicists. So here is what it comes down to. One machine, 4 watts a year, draining away on a schedule nobody can renegotiate. 15 billion miles of empty space between it and everyone who built it. 23 hours for a question to travel out, and 23 hours for an answer to come back. Something is slowing Voyager 1 down. It is the sun, still holding on, 10 billion times more gently than the ground beneath your feet. And there are smaller forces layered underneath that. The push of its own escaping heat. That took 30 years. A lost archive of magnetic tapes. And a full thermal reconstruction of a dead spacecraft to finally pin down. We got the answer for Pioneer. We do not have the measurement precision to ask the same question of Voyager. And when Voyager goes quiet sometime in the 2030s, we lose the chance to ask it at all, at least for a generation, because nothing we are currently flying will be out there to replace it. One machine, 4 watts, one chance to listen. The question is whether anyone is paying attention. If you want more of this, Real missions, real numbers, real unknowns, stated out loud. Subscribe and turn on notifications. Everything here is grounded in real published research, rather than exaggerated headlines. And if we do not know something, you will hear me say so.